just as the RC circuit is one of the most important applications of first-order linear differential equations, surely one of the most important applications of second-order linear differential equations is the RLC circuit. And the importance of RLC circuits actually comes from, surprisingly enough, their ability to resonate. Okay, and we're going to talk exactly about what that means today. So let's first start by just drawing a RLC circuit. So we're going to consider circuits that look like this. So we're actually going to start with a voltage source. And the voltage source I'd like to consider today is actually an alternating current voltage source, so an AC voltage source. And that essentially means that it's going to provide a voltage that oscillates back and forth in both directions. So this is this is an AC voltage source. That's a symbol for an AC voltage source. And let's say that the voltage is given by some function v of t. Okay, so our first component will be a resistor. Okay, there's our resistor. The next component is a capacitor. Then we're going to follow that up with our final component, which is called an inductor. And here's a symbol for an inductor. Okay, and then we'll connect it back up to the AC voltage source. So that's our RLC circuit, and this is a series RLC circuit because the components are all connected in order here. A series RLC circuit. And we actually already derived the differential equation for this. We did it in the very first lecture on second order linear differential equations. We talked about the RLC circuit, but I just want to quickly recall how we get the differential equation. And it comes from Kirchhoff's second law, which says that if you go around any closed loop, the voltages are all going to sum to zero. So the voltage drops across each component is going to, they're going to sum to zero. And so first we have v of t. The voltage is increasing by v of t here, although sometimes it might be negative, and then we interpret that as decreasing. But okay, so we have v of t. And then we have minus IR. That's the voltage drop across the resistor. We have a minus sign because the voltage is decreasing. So very important that we include everything with its correct sign. And then across the capacitor, the voltage drop is Q over C, or Q is the charge. That's what we want to study. And then across the inductor, the voltage drop is actually, it turns out to be proportional to the derivative of the current, di dt. L is the constant of proportionality called the inductance. And yeah, Kirchhoff's second law tells us that this equals zero. So this is by Kirchhoff's second law. Right. Okay. And let's also recall that there's a relationship between Q and I. Namely, I is the derivative of Q. So the current is defined to be the derivative of the charge, the time derivative of the charge. Okay, and so given this, we get a second order differential equation in Q. So here's our differential equation. L times Q double prime. This is Q double prime. I'm moving all these to one side. And then we have plus R times Q prime. I is Q prime. Plus 1 over C times Q. And that's going to equal, we'll leave V of t on this side. That equals V of t. Okay. And let's actually be more explicit about v of t. So we said we want that to be an oscillating voltage. So it could be a sine or a cosine, for example. Let's just let's suppose that this v of t is actually well, there's some amplitude, maybe alpha, and let's say it's a sine of omega 1t. So we'll use that same notation as last time. We'll call the the frequency of this forcing function, omega 1. Okay. So first thing I'd like to mention is often we actually want to write a differential equation for the current. We want to study the current rather than the charge. But that's not difficult to do. So yeah, let's ask this question. So what differential equation does the current satisfy? I'll give you a second to think about how you might do that. Okay. Well, what we can do actually is we can just take this differential equation here, and if we take the derivative of both sides, then we end up with a second order differential equation for the current. So here's what I want to do, in other words. I just want to take the derivative with respect to time. And what do I get? I get L Q triple prime, but Q triple prime is I double prime. Right? So I double prime. Plus R times I prime, plus 1 over C times I. Right? Derivative of Q is I. Notice the derivative distributes over the sum like this, so we can do it. And that's going to equal, and we have to be careful, we have to also take the derivative of this function here. And that's going to be A omega 1 cosine omega 1t. Okay, so we're actually going to be studying this differential equation today. And one thing I'd like to recall from last time is, how does this work if R is 0? So that's what we studied for the previous two lectures. So let's just recall that really quick. So recall, if R equals 0, how do we interpret this, by the way? What's happening if R is equal to 0? Well, it's just like the mass spring differential equation, but without the damping. Right? So we have an undamped mass spring system. And so we just get an oscillation back and forth that never dies down. Okay, but we also have this term over here. So we're forcing our mass spring system to oscillate back and forth with this frequency omega 1. And previous two lectures were devoted to sort of understanding what happens in that situation. And the most interesting case is resonance. So when does resonance happen? So we get resonance when let me just write out our equation. It's easier to picture. So R is 0, so I'm just going to get rid of that term. Okay, so when do we get resonance? We get resonance when this frequency here of the driving force matches the natural resonant frequency of the system. And so it's when omega 1 equals omega 0. Omega 0 is the natural resonant frequency of the system. Well, what is that explicitly here? So what is omega 0? Well, we don't have to solve the differential equation. So let's just take the homogeneous equation. And then I'll divide by L to get this. And recall from last time, we noted that when you write a differential equation in this form, I double prime plus some positive number times I, right? How do we interpret this number right here? What is the meaning of that number? So it's not the frequency itself, but it's the square of the frequency, right? So here we have omega 0 is 1 over square root of LC. So let's include that up here. And let's graph a typical solution to this differential equation here. In the case where where omega 1 is chosen to be exactly that number. And remember what happens, we get a function that looks like this. So this is what the current is going to look like here. Its amplitude is ever increasing. It's increasing linearly. So you actually get an unbounded amplitude. Okay. So this is a solution to this differential equation here. Here's the current. This is a solution when omega 1 equals omega 0. Okay. Okay. So this is actually a bit scary, because what will happen to our circuit eventually, if the current is just going to increase unbounded, then eventually the circuit is just going to burn out. So we might think that resonance is something to avoid. But it turns out that this property is actually what makes RLC circuits so useful to us. And the first thing I'd like to emphasize is that this picture right here actually just never happens in real life. So yeah, if R equals 0, we get resonance in this case. But in real life, R is never 0. Okay, R is never 0 in real life. There's always some resistance, or in our mass spring system, there's always some damping. Right? If there were no damping, then you could just make a perpetual motion machine, which we know is not possible to do. And you might say, well, what if we try really hard to make a LC circuit? What if we just don't include any resistor? And it turns out even if you try to build an LC circuit, you still end up with an RLC circuit. And that's just because even just the wire here has some resistance, and these components themselves have some resistance. So LC circuits only exist in theory, not in real life. So we're going to consider this equation today, where R is actually greater than 0. So let's write out our equation one more time. So Li double prime plus Ri prime plus 1 over Ci. We have A omega 1, alpha omega 1, cosine omega 1t. What does the general solution to this look like? Okay. Just abstractly. We don't have to write down exactly what it is. We can't write down exactly what it is because we don't know which of the cases that we're in. But the general solution, abstractly, it's going to look like, yes, I usually say YH plus YP, but here we have the current, so it's IH plus IP. There's a homogeneous general solution, and then there's a particular solution to the inhomogeneous equation. Okay. But something really nice is going to happen. Okay, so if R is positive, so if R is not 0, but it's positive, so this is basically any circuit you build in real life is going to have some resistance. What is going to happen here? So IH is actually just going to go to 0. If R is, then IH is going to go to 0. Okay? As t goes to infinity. No matter what. No matter whether we're critically damped or underdamped or overdamped, this is always going to 0. And so the long-term behavior is going to look like IP alone. So I'll write that out. So the long-term behavior will look like IP, and we call that the steady state because it persists. This IH we call the transient. Okay, and in particular, what is IP going to look like for our equation? Well, our guess for IP is going to involve cosine and sine terms, and that guess will always work because, again, we have some resistance here, so we're never going to get pure sines and cosines for IH. So in particular, IP is going to look like an oscillation. So yeah, it'll look like IP, which is an oscillation. Okay. Okay. However, some interesting things can still happen. So it turns out that if you tune this omega 1 exactly right, then the amplitude of this resulting oscillation can be unexpectedly large. And so that's what we call resonance. So resonance occurs. So we never actually get this picture in real life with an unbounded amplitude. But resonance occurs when, let's say, yeah, our driving frequency, so omega 1 is chosen. So that the amplitude of this oscillation, or of the steady state, right, becomes unexpectedly large. Okay. So what's the picture of that? So maybe our maybe here's what my my function. So maybe here's what alpha omega omega 1 cosine omega 1 t looks like. Maybe it's just something like this. Oh, I guess I drew a sine, but that's okay. I have some oscillation. And then resonance occurs when our steady state solution, which is IP of t, IP, is going to look something more like this. Okay, so large increase in amplitude. So let's study this more precisely now. So what I'd like to do now is, I actually don't care so much about IH because it's going to 0. I really care about IP. So I want to figure out what IP is. In particular, it would be great if I get a formula for the amplitude, at least, of IP. So yeah, let's derive a formula. Let's find a formula for the amplitude of the steady state. Okay. All right. Well, we know how to do that. So let's guess. Let's guess. IP is going to be, well, what should we guess? We should guess cosines and sines. Right, so let's say A cosine omega 1t of the same frequency, of course, plus B sine omega 1t. Okay. And you should actually try this. It's good to try it at least once. So you take this, take its derivative, second derivative, plug them into the differential equation, try to figure out what A and B are. But I say you should only try it once because the math gets extremely nasty. There's just a lot of algebra. So rather than just tell you the answer, I'm going to do this another way. So here's another way to get the particular solution. I'm going to do what's called complexifying the equation. So to complexify the differential equation. Okay, what do I mean by that? So here's our differential equation. And whenever I see a cosine, the first thing I think is that this is actually just part of an exponential function. Right? This is the real part of the complex exponential. So So our whole equation, you can view this differential equation that we have as the real part of a complex differential equation. So it's the real part of this equation. L I double prime. I'm now thinking of I as a complex solution to the differential equation. Plus R I prime plus 1 over C I. And instead of the cosine, I'm going to put the complex exponential. So alpha omega 1 e to the I omega 1t. Right? So by Euler's formula, e to the I omega 1t is cosine omega t plus I sine omega t. And so this is the real part of this complex exponential. And I'm going to solve this one instead. And this is a nice method because exponentials are really nice to work with. But we should keep in mind. So we will need to take. So yeah, let's guess our particular solution first. So we're going to guess. Well, what do we guess this time? We shouldn't guess sines and cosines. We should just guess an exponential, and it should have the same sort of parameter up here. So I'm going to guess a times e to the I omega 1t. And I'll take its derivatives. So the derivative is, well, this all comes outside by the chain rule. And the second derivative, well, I get an I squared. That's negative 1. So I can write this as a omega 1 e to the I omega 1t. But I should mention one thing. So this will be our solution to the differential equation, but it will be to this differential equation. If I want a solution to this differential equation up here, I will need to take the real part of this. We'll need to take the real part to get back to a solution to this differential equation. Take the real part to get a solution to the original differential equation. Original differential equation. Okay, so we'll have to remember to do that. Okay. Well, let's plug this in. So I'm going to plug this in here. But I'm already noticing that every term is just going to have this e to the I omega 1t, right? So I guess I don't even need to write those. So what do we have first? We have this one. So we're going to get minus L a omega 1, right? Well, I think I messed up here, right? I should an omega 1 should come down here also. So I actually get an omega 1 squared. Okay. And then I have a r times this one, r times a I omega 1. And then plug this one in here. So I have a 1 over c a. And that equals alpha times omega 1. And I want to solve for a. So what is a? Well, I can factor out the a and then just divide by what I have left. So try not to mess this up here. So to divide by minus L omega 1 squared. Oh, there's a lot here. So plus R I omega 1, right, plus 1 over C, like that. Okay. But that's exactly what we wanted, right? So that's our coefficient here. So here's our solution. So yp is, I suppose I should be calling it ip here, but I guess you know what I mean. So yeah, I should have put ip. Oh yeah, what is this going to be? So it's a times e to the I omega 1t. It's r I omega 1 plus 1 over c times e to the I omega 1t. But as we said before, we need the real part of this. We need the real part And that will be our particular solution. Okay? Because this solves that differential equation, so the real part will solve this differential equation. This differential equation being the real part of this differential equation. Okay. Okay, so how do we do that? Turns out we aren't exactly done yet because we need to first write this in a plus bi form, but this should give us some good practice, right? So I'm going to I'll just take 1 over this thing and then try to rewrite that. So I have L minus L omega 1 squared plus 1 over C. I'll write the real part there. And then the imaginary part of this denominator is I times R omega 1. And now we remember the trick. We have to multiply this by the conjugate of this complex number here over itself. And that will cause the denominator to, the imaginary parts of the denominator to cancel. So we need to multiply by minus I R omega 1. Right? So let's put that up here too. Okay, and what we get is, well, in the numerator, we just get this. And then in the denominator, something nice happens. So if we did this right, all the imaginary parts should cancel. And so what is the real part going to be? Well, it'll be that one times this one, which is, well, I can just write it as this quantity here squared, right? And then I will also get something real from this one times this one. And then the other two combinations will cancel. So I R omega 1 times minus I R omega 1. I times I is negative 1, and I have an additional minus, so I have plus R squared omega 1 squared. Right? Okay, so that's just rewriting this 1 over this thing. But I have this alpha omega 1 still. And yeah, let me write this denominator. Okay. And then the numerator I'm going to write over here. And then I need to multiply that by this, right? Because this is sines and cosines. Let's actually use Euler's formula. So cosine omega 1t plus I sine omega 1t. So I want the real part of this thing right here. This is already a real number. That's why I separated it out. So we don't have to worry about this. This will definitely be included in the real part. What is the real part here? Well, this part here times that part there is going to be something real, right? So let's write out what that is. So I have a minus L omega squared plus 1 over C times the cosine. Need another set of parentheses there. And then what else is going to get me something real? Surely not this one times that one, right? I'll have an I. And not this one times that one. But if I do, again, this one times that one, I will get something real. And that something is plus R omega 1 sine omega 1t. Okay. So I think we are finally done. So here, I'm just going to say, take the real part, and we get this. I'm not even going to write the imaginary part because we don't care about it. And we have this factor out front. Okay. Phew, so we are finally done. We finally have YP, our particular solution. So this is supposed to be a solution to this equation here. And you might think that was that was quite a lot of work, right? I feel like it's going to be even more work if we guess this. So I think we actually saved some work by going to complex numbers. But yeah, in any case, we have yp now. Okay, what are we interested in here? We're interested in the amplitude. We want the amplitude. The amplitude of this solution. Okay, well, what is the amplitude? So it's not so obvious just looking at this. And that's because we have sines and cosines, a sum of a sine and a cosine. So that's not the amplitude by itself. That's not the amplitude. This thing by itself is not the amplitude. First, we have to write this sum of sine and cosine as a single sine or cosine. But luckily, in previous lectures, we worked out all the formulas. So this is like my C1, and this is my C2. Yeah, so we have C1 cosine omega t, omega 1t, plus C2 sine omega 1t. We can rewrite this in the form. The amplitude, what is the amplitude? Our formula for the amplitude is C1 squared plus C2 squared, and then take the square root, times a single cosine of omega 1t minus phi. So we have some phase shift there. And we don't really care about the phase shift. All we're after is this amplitude. So let's write out what C1 squared plus C2 squared is. And then, of course, we still have to multiply by this. So let's multiply by this. Yeah, this lecture is getting very computation heavy, but I promise there's a payoff at the end if you stick around. And I don't want to try to hide any of these computations from you either. So what do we get? We get a square root of C1 squared plus C2 squared. Okay, that's our amplitude. Okay, so this is the amplitude. The amplitude of yp is this number, is this function right here. I guess we can think of this as a function of omega 1. Okay, well, what do you notice here? So what I notice here is this is the same exact expression as this, right? Only this one has a square root. So I have something to the 1/2 power, right, the square root, over something to the first power. So I get a negative 1/2 power. So I can actually rewrite this as alpha omega 1 over, the square root is now in the denominator, and I get, it's just this expression inside. This is a really important expression down here. We can do one more thing. Why don't we try to cancel out some of these omega 1s, okay? So how do we do that? Well, we can factor out an omega 1 from here, but then it'll end up in the denominator there. And it'll actually get squared when we take it out of this square here. So we'll have an omega 1 squared. That we can take out. Right, we have an omega 1 squared in both of these terms. We can take that out and cancel it with that omega 1 in the numerator. So let me try to write down that what we got. So I just took out an omega 1 here. So this is just minus L omega 1, not omega 1 squared, plus 1 over C omega, and that is squared. And then I have plus an R squared. Okay, I think this is as simple as we can write it. Great, so let's box this. This is the fruits of our labor for past half hour or so. But this is the amplitude of the steady state solution. And we would now like to analyze this. So let me get one more page. Okay, what is going on here? Okay, let's actually call this, let's give it a name, the amplitude of yp. Let's call it A of omega 1. We'll think of it as a function of omega 1. This should be an omega 1 down there. Okay. Let's try to sketch a graph of this. Maybe I'll do it over here. Okay, so we're going to graph this function. And I mean, you might say, well, how can we graph this function? We have all these variables. So I'm just going to imagine we fix R, C, and L and sketch a sort of typical graph of one of these functions. First of all, what happens when omega 1 is 0? Well, you can't really plug it in here, right? You get something infinitely large in the denominator. You might think that's going to equal 0. I guess we can plug it in here, right? But we're also plugging it in there in the numerator, so we actually get 0. So when we plug in 0 for omega 1, we get 0. And then after that, it's always going to be positive, because this thing inside the square root is a sum of squares. That's always positive. And so what we have here, it's going to be increasing, and then maybe we're not sure what happens in the middle. But the next thing we can ask is what happens when omega 1 gets very large, right? So now we should look at actually this version. When omega 1 gets large, well, this part here gets very small, but this part gets very large, right? We're adding something small. That doesn't affect it. This is still very large. It's very negative. But then we're squaring it. It's a large positive number. Whatever the resistance is, doesn't matter. We have the square root of a very, very large number. And alpha is fixed. So we're dividing by a very, very large number. So it's actually going to go to 0, the amplitude. Okay? And so the question is, what is happening in between? And it turns out that we get something like this. So this is actually going to increase. It's going to be a maximum at some point, and then it's going to go back down. And what we would really love to know is, when do we get that maximum? So what is this value of omega 1 that will give us the maximum? And it turns out it's going to be a very familiar value. So let's do a little bit of calculus, because that's how we find maximums, right? And minimums. We take the derivative of this alpha omega 1, and we set it equal to 0, find critical points. I don't feel like taking the derivative of this function. I don't know about you, but it's a bit of a complicated function. So let's actually just note that the numerator is a constant. And so this will be at a maximum exactly when this thing in the denominator is at a minimum, right? So let me write that. So this function is maximized. When this denominator, you can even get rid of the square root, right? You can just say when this thing inside the square root is at its minimum, right? When, so yeah, let me even get rid of the square root. We want to actually minimize this function here, okay? Is at a minimum. Okay. Let's give this a name. So here's our denominator. Okay, this is not going to be bad at all to take the derivative. We're taking derivatives because we want to find critical points. That will be a candidate for the maximum. Derivative by the chain rule is 2 times this function in here times the derivative of this inner function. It's a function of omega 1, right? Omega 1. What's the derivative? Derivative, this first part is just minus L, and then the second part is going to be minus 1 over C, and then I have an omega 1 squared by the power rule. Because this is omega 1 to the negative 1. So I get a minus omega to the negative 2 times C. And the R just goes away. It's a constant. Okay, and I want to set this equal to 0. I want to set that equal to 0. Well, what value of omega 1 makes this 0? Well, if I look at this second part here, everything here is positive, right? L is positive, omega 1 is positive, C is positive. So then this thing here is never going to be 0, right? It's going to be a negative number. So I have minus L, minus 1 over omega 1 squared C. So yeah, this part here is just never 0. Which means I can just focus on this part here, right? What about this part here? So let's write that down. So we get this. Okay, so then 1 over C times omega 1 equals L times omega 1. So we multiply and we get omega 1 squared is 1 over LC. So omega 1 is, this should look very familiar. Omega 1 is 1 over square root of LC. That's exactly this number. So that was exactly the natural resonant frequency of, not of this system, but of the idealized system where we didn't have any resistance. Right, so it's the natural resonant frequency of this system, just the LC circuit. So you don't want to, so you have to be careful here. So omega 1 is not, this is not the quasi-frequency of this differential equation. Right, that's going to involve R also. But this is the natural resonant frequency that you just get by from this equation here. So it turns out this right here is 1 over square root of LC. So when omega 1 is tuned to be exactly this, we don't get an unbounded amplitude, right? This is bounded. It's some fixed number, but we get some very large amplitude of the oscillation. So here's how to interpret this picture. This is not a solution to the differential equation, but each value of omega 1 corresponds to some differential equation, right? Some forcing function. And then we can look in turn at the steady state response. So for example, a point like right here, let's say, I do it in another color. So let's say this point here, that might correspond to a picture that looks something like this. So here's maybe a fairly small amplitude, right? So this is my graph of the particular solution, IP. And then maybe a point here. What will this give me? So again, this axis represents the amplitude of the steady state response. So if I choose a frequency like this, that's a little bit higher or a little bit lower even than my resonant frequency, I get a higher amplitude. So I get something that looks like this. Same frequency, they all have frequency omega 1, but I get a higher amplitude. And finally, if I pick a point way up here, I get a very large amplitude. If I'll draw it really large like this. So I get something more like this. And that's really what resonance is. Okay. So I don't get an unbounded amplitude, but I get a very, very large amplitude relative to the amplitude I started with, relative to this alpha here. Few things we can consider now. The first is, what happens when I change R? All right, so let's grab our formula. What happens when I change R? Right. So imagine that I'm here at this spike. So I plug that in, and I actually get 0 for this part. Right? That's actually the same thing here. This is 0 at this frequency here. So then this just becomes alpha over R. And so as I decrease R to 0, this actually goes to infinity. And so one thing that happens is if I want this spike to get higher, I can decrease R. Okay. Okay, so what's the point of all of this? How is this useful? So imagine we have a circuit like this. And suppose that this voltage source is actually supplying our circuit with various different signals of different frequencies. So we have many different omega 1s that we can input. Okay. Each of those omega 1s is going to correspond to a picture like this, right? So we'll have some current in the circuit, and depending on what omega 1 we feed in, we'll get different amplitudes. Okay. And so what we can do is we can actually design the circuit to respond more favorably to certain amplitudes. That's what we can do here. So so let's write this out. So by choosing the parameters of the circuit, so R, L, and C, strategically, what you can do is you can design a circuit to basically to respond favorably to a certain range of frequencies. Okay. Certain range of frequencies, while ignoring others. Okay, so in this picture, if omega 1 is, say, within this range here, then I will get a very large amplitude for the current. Okay, I'll get an even larger amplitude if I'm close to this frequency here. We call that the resonant frequency. And if my omega 1 is too far away from that resonant frequency, I will get a very small amplitude for the current. And it turns out that if you change R, L, and C, and this is something that you study in electrical engineering, you can actually manipulate this graph. So you can make this spike narrower like this, or wider. You can increase the height of this spike. We already talked about how you could do that just by decreasing the resistance. You can move this spike back and forth. The way you do that actually is by changing the capacitance. And so actually one really important application of this is in radio transmission. So when you get a signal actually when you turn the dial on your radio, what you're actually doing is you're changing the capacitance. And so you're actually moving this spike, essentially. I mean, this is a simplified model, right? This is the simplest possible RLC circuit that we can write down. But essentially what you're doing is you're moving this spike And that allows you to receive certain frequencies more favorably than others. And this is sort of the key behind radio transmission. This is how radios work. So yeah, this is just a very brief intro to RLC circuits. You can study these pretty much endlessly. But yeah, I hope this inspires you to take a look at this fascinating subject sometime in the future.